So, concept zero, the Big Bang, okay, did not have a good name. They called it the Standard Model. They called it all sorts of things. But I think an astronomer named Hoyle, who, by the way, did not like the Big Bang, referred to it as the Big Bang. Yes? And this is actually, that's irony. In trying to shoot down the theory, he actually gave it a name which stuck, which was a good name, okay, because the Big Bang Theory states that all of this universe, everything that is here, all of this space itself, emerged from a singularity, a point in space. And now we think that happened about 13.7, plus or minus, I think, 0.2 billion years ago. And so if somebody says to you, if they ask you this question, they say, well, where did the Big Bang happen? Okay, understand that every place that is now, space itself, emerged from the Big Bang. And so you can, of course, look at them right in the eye and say, they'll think you're crazy. It happened inside, right in the center of this optical mouse. Right? You know, it happened over there. It also happened in New Jersey, I hear, right? Because all of this was in the space, right? So the Big Bang is a universe that expands out of this singularity. And it expanded very, very fast, and that's the whole thing. And pretty much, I mean, you might hear like stories that the Big Bang is in trouble, the model's got problems. Gentlemen, I will move one of you. Maybe it's Jacob's turn this time, I don't know. Okay, this notion that maybe the theory is in trouble, but it really is the only game in town. Okay, there's so much evidence. And I used to do this whole thing about, you know, God and religion and this and that. But my own theory, my 30-second take on religion and stuff like that is I think there's really two ways to know the universe, right? There's faith, which is a belief in things that can't be proven, but we know to be true. And then there's science, which is the exact complement of that, right? Which is a belief in things, only things that can be proven, right? And so I really don't want a religious person telling me about nucleosynthesis, right? Okay. But I also don't want a physicist explaining why a poem is beautiful or a song is good. Yeah? Don't you think both of those are bad ideas? I don't know. Anyway, so I had a kid who was sort of an interesting thing because he came in and we were talking about the Big Bang and he was like, no, I know it didn't happen, right? And by the time of the period where I knew him, he said, well, you know, I still think God created the universe. He just created it using the Big Bang, which is, of course, where most of the physicists that talk about the Big Bang, where they're coming from. These are precepts largely taken out of Timothy Ferris's very good book, and he wrote, if you are more interested in this sort of stuff, it's The Whole Shebang. And I don't know if it's been updated. The version I read was written in 1997, and we've learned a whole lot since 1997. Okay, so, but it's by Timothy Ferris, and he could pretty much write a book about lawnmower maintenance, and it would be just riveting. Okay, so I highly recommend if you're interested in sort of stuff like that, this is a very good book. Brief History of Time, Stephen Hawking is also very good. And there's actually Bill Bryson wrote a really good book too, A Brief History of Nearly Everything. Do you know that one? Yeah? Okay. But anyway, do you need this? Yeah. All right. There you go. Jen's got a question. Oh, the Brief History of Bryson's book? It's like that. Hawking's is thinner, a little more hard to understand. Yeah. He gets into like space-time diagrams and stuff like that.
Theory that basically time is infinite.
Not really. We think time began 13.7 billion years ago, but you know, there it is. Yeah, it's kind of crazy. Okay, but anyway, this is Timothy Ferris, and these are the precepts. Basically, these are the ground rules, and if these are not true, if all of these are not true, then cosmologists don't want to play, right? And so basically, we think the laws of physics are the same. If the mass of a hydrogen atom here and the spectral lines of a hydrogen atom here on Earth are the same as those of a star 10 billion light years away, right? That's the basic idea there. And if that's not true, then, you know, who knows, right? Okay. The universe is expanding. It's very hard to say that it's not expanding, right? Isotropic and homogeneous. Homogeneous means that it's the same everywhere. That if you got it's like ice cream, right? All the raisins aren't in the bottom of the bucket of ice cream. You get as many raisins with every scoop of ice cream, right? That's homogeneous, right? So if you scoop the universe somewhere, you'll get the same amount of matter everywhere you scoop it. Isotropic means there's no trend. The air in this room is not isotropic. There's a higher pressure at the bottom, lower pressure at the top. Okay? So there we have it. So the universe doesn't have a trend. It's not like there's more cheese that way and more crackers that way or something like that, right? You know, and homogeneous means that it's not like all the matter's in like these clumps. It's spread out. Yeah. Only this is, by the way, getting less and less true because where there's large-scale structures that we don't really understand, right? General relativity works as long as you stay away from singularities, like black holes, right? The early universe is hotter than it is today. More about that in a little bit here, right? That the universe is changing, right? Evolving just means to change. And then the cosmological principle states that if your theory works only if you are in a special time or a special place, right, then it's not likely to be true. Like Ptolemy's model. Did you guys study early models of the solar system? What's Copernicus's model? Copernicus's model is largely what we think happens today. The planets orbit the sun, right? What did they think before that? Yeah, the sun goes around the Earth. The planets, by the way, do amazingly complex things. Ptolemy had a model for how this worked, right? How the planets could do these crazy gyrations as they went around the Earth, because Mars has to go forward for some period of time, then backwards. It does retrograde things, right? Ptolemy is like the poster child of the violation of the cosmological principle, that you have to be in this very special place, and then only then does it work. And then obviously, you know, there we have it, right? Okay, so those are things that we have. So let's go into history of the Big Bang, right? Relativity says that the universe has to expand or contract, right? In the 20s, Hubble discovers that the universe is expanding. And then if you have the universe is expanding, if you go backwards in time, the universe must be? In the past it was smaller, yes, there we go. And in the future it is bigger, right? If you go back far enough, I mean, we know how fast it's expanding now. If you go back far enough, it gets really small, doesn't it? Yeah, now there's a principle in physics that states that if you compress a gas, it gets hot. You know this because compressors get hot, do they? Yeah? When you pump up a bike tire, the pump gets hot. Yeah? Diesel engines compress gas till it gets white hot, and then they just inject diesel in there and it goes boom, right? Okay, so if you take a universe and you compress it and make it smaller, it gets hotter, right? And so basically they said, gee, we think the universe emerged from this big fiery explosion. Who knows why, right? You know, okay. So if it was once small, right? If it was small, it was hot. If it was hot, it should be a little bit warm now. So these guys predicted that if you looked in any direction, because if all of the universe came from a singularity, well, if you look away from Earth in any direction, aren't you just looking back in time? Aren't you? If you look at something 100 light years away, you're looking at stuff 100 years ago. Yeah? It's kind of a crazy thing, right? And if you look back far enough, you ought to be able to see, and in all directions, if the Big Bang is correct, in all directions you should see a big fiery wall. You should see the universe as flames in the sky. Right? Only what they did was they predicted that this radiation, the wavelengths of light, should be stretched out with the universe, and they should now be microwaves. Right? They started out as light, very high energy light waves, right? And now they've stretched out and they are microwaves. They're like this long. Yeah? Right? They've been stretched out from being 100 times bigger than atoms to now being like this big. Right? Okay? And this Wien temperature, this is that thing about temperature and brightness, and then the black body radiation that we talked about, right? So these are predictions that they made in the 30s. Of course, in the 30s, well, what else were we preparing to do? And in large quantities and all over the world. Yeah, weren't we getting ready to like kill people? Yeah, this is like, you know, World War II is gearing up. Yeah? Okay? So basically at this point there were two problems with his theory, right? But basically he said, look, if you look in any direction, you should see this big fire explosion. It should look like a warm object anywhere you look in the sky. And this is why, because the universe emerged from this big explosion, right? There's only two problems with this. One, we were getting ready to fight a war. And then the other problem was that there was no way to detect in 1930 microwaves, right? So everybody said, oh, that's interesting. That's an interesting prediction that we will someday prove, right? Yeah? So let's fast forward a little bit, huh? Okay. Okay, there's this old guy living in a hut in Vermont, and he's very hard of hearing. And no, just kidding. Okay, this is a radio telescope.